Hi, it's Mr. Anderson, and this is AP Physics Essentials video 57. It's on the strong nuclear force. Remember, there are four fundamental forces in the universe. We've got gravity and electromagnetism. They both operate at all scales, with gravity dominating at the large and electromagnetism dominating at the small. But we also have the strong and the weak nuclear force, and it took scientists a while to figure that out, just because we don't live at the scale of a nucleus. And so how is a strong nuclear force different than the others? Well, unlike gravity and electromagnetism, it only dominates at the very small scale. It's way stronger than all the other forces, and it's what's holding the nucleus together, and then the components of the protons and neutrons inside the nucleus as well. And so the fundamental problem scientists saw right away with the nucleus is that if you have two positive charges, and protons are going to be positive charges, next to each other, according to electromagnetic forces, they should be pushing themselves apart. We should have repulsion. But they don't just go flying apart, they're held together. And so there must be a force, and we call that the strong nuclear force holding it together. It's the greatest of all the fundamental forces. Something like 130 times that of electromagnetism. And so once we get to this really small scale, and that's where strong forces are going to operate, it's going to take over. Now, how small do I mean? On the order of a femtometer, which is 1 times 10 to the negative 15th meters. And so once we get to the level of a nucleus, there's going to be a strong nuclear force, and this is a force between all of the components of the nucleus, both the protons and the neutrons, and it's holding it together. And even at a smaller level, if we look at the components of those nucleons, the quarks, it's holding those together to make the protons and the neutrons. And so how does a strong nuclear force work? What we think is going on is that mesons are going to be exchanged between these two protons. And so a meson is a quark and an antiquark, and it'll kind of bounce between the two, almost like a ping pong ball, and it holds them together. So we have this strong force holding them together. Not only protons, but neutrons as well. And you know this, that if we zoom into a proton itself, it's made up of all these quarks. And what's holding that together? We have these gluons that are literally gluing the proton together. And so the strong nuclear force is even greater when we get to this small scale. And so we really have two worlds at play here. If we have two protons that are far enough apart, electromagnetism is going to push them apart. But once we get to the level of the strong nuclear force, it's going to pull them together. And how big is this circle here? It's about 2 femtometers apart, or it's about 2.5 diameters of a proton apart. And so what happens is, as we push this proton close, electromagnetism is going to be that repulsion you see, but once we get inside that barrier, that strong nuclear force is going to pull them together. And so where's an example of us seeing that in science? Well, you could look inside the nucleus itself. And so if we're going with an atom that we're familiar with, like hydrogen, hydrogen has 1 proton, and so it's going to sit inside this binding area of the nucleus. What's binding it? It's going to be the strong nuclear force. But let's move to something like helium. Helium is going to have 4 nucleons here. And so what happens when we have 4 nucleons? We have greater force, strong force between all of these. And so you can see that the binding energy, if we're looking at helium, is going to increase. If we increase the number of nucleons, if we're looking at helium, for example, there's still a small nucleus because it's pulling it all together. But what eventually happens is, once we get nucleons inside there that are starting to move outside of this scale, and you can see on this graph where that occurs, once we go past iron, now the strong nuclear forces aren't great enough to hold that together. Now electromagnetism starts to take over, and that's why we start to have radiation occur. These aren't stable anymore, and so we're starting to lose bits of that nucleus. And so did you learn to identify the strong force as the force that holds not only the nucleus together, but the components of the nucleus together? I hope so, and I hope that was helpful.